This is the Enigma machine. It looks like a typewriter, but it has a very different purpose. During World War II, it was used to keep messages secret, or in other words, encrypted. In this video, we'll look at why the Enigma machine exists, how it was used, and then we'll take a look at the inside to see how the mechanism works. This video is sponsored by Brilliant, a fun and interactive way to learn math and science. Towards the end of this video, we'll take a closer look at their website and app. While making this video, I had a lot of help from enigmamuseum.com. These guys took apart an actual Enigma machine and showed me what's on the inside, behind the panels, all the inside wiring, and how each mechanical piece works. This would have taken a lot longer to 3D model and animate without their help. So big thanks to enigmamuseum.com, and now let's get to some animation. To really understand the Enigma machine, we need to understand something called encryption. Let's use an example. Say we have two friends, Alice and Bob. Alice wants to send a message to Bob. However, Alice doesn't want anyone else to be able to read this message, such as Eve. Just as an example, we'll keep the message really simple. Alice will need to scramble the contents of the message. This is called encryption. It looks like a bunch of random letters, and if Eve gets a hold of it, then she won't be able to understand it. When the message gets to Bob, he needs to unscramble the message. This is called decryption. Now he can read the original message. Alice and Bob need to agree on a way to encrypt and decrypt their messages. A real simple way to do this is called a Caesar cipher. This involves shifting all the letters in the message 3 spaces to the right in the alphabet. So an H becomes a K, an E becomes an H, an L becomes an O, an L becomes another O, and an O becomes an R. Now the message looks like gibberish, a bunch of random letters. When Bob gets the message, all he has to do is take each letter and move it back 3 spaces. This will give him the original message so he can read it again. Now Eve in the middle, as long as she doesn't know how the messages were encrypted, she won't be able to read any one of them. During war, encryption is extremely important. Commanding officers need to be able to get messages out to the troops on the battlefield, but they don't want the enemy to be able to understand these messages. Nowadays, encryption is performed by computers, but this wasn't always the case. The Enigma machine was used to encrypt and decrypt messages. You can think of this as a very sophisticated letter scrambler. It was invented in the early 1900s, and then most famously, it was used by the German military in the 1930s and throughout World War II. This is the keyboard with 26 letters. And this is the lamp board, which also has 26 letters, but these letters can light up. Each time you press a letter on the keyboard, a letter on the lamp board lights up, but it will always be a different letter than the one that was pressed. There are usually 2 people involved when the machine is used. One person to type in the letters, and another person to write down the letters that appear on the lamp board. Let's use our example from earlier. Type in each letter, and write down the letters that appear on the lamp board. Now we have our encrypted message, the scrambled letters that nobody can read. This message is sent usually by radio using Morse code. The person who receives this message also has their own Enigma machine. To decrypt the message or unscramble it, they type in the letters on the keyboard and write down which letters appear on the lamp board, and out comes the original message. The Enigma machine was used for both encryption and decryption. The person sending the message needs a machine, and the person receiving the message also needs a machine to be able to read it again. So how does the Enigma machine know which letters to give you? Maybe you press an A and out comes an H. How does it do that? Well, part of the answer is electricity. Let me show you a simple example. We have a battery, some wires, and then something that uses electricity. In this case, a light bulb. This is called a circuit. It's a closed loop for the electricity to flow. But if there's a break in the wire, then the light bulb turns off. If we put a switch in here, now we can easily turn the light bulb on or off. There has to be a complete path for the electricity to flow. Now let's add another path, one more switch and a light bulb. Now we can turn on 2 different light bulbs. Depending on which switch we turn on, there's a different path through the wires. We could expand this even more. more switches, and more light bulbs. Now, this is predictable. We know which switch goes to which light bulb. But what if we scramble these wires? Now, the switch for the letter A turns on the letter C light bulb, and the C switch turns on the B light bulb. This idea of scrambling the wires, that's how the Enigma machine works. Let me show you on the real thing. The battery is inside in the top right-hand corner of the machine. The keyboard has 26 keys. When you press one of them, it connects a circuit which will then turn on one of these 26 light bulbs. The light bulbs will then illuminate the letter that's directly above it on the lamp board. When you release the key, the circuit is disconnected and the light bulb turns off. Each key connects a different path, which means a different light bulb. Okay, this is the challenging part of the video, understanding the circuit, or the path that the electricity follows throughout the Enigma machine. Maybe pause the video, get your degree in electrical engineering, and then let's do this. The three main parts that we need to understand are the rotors, the keyboard mechanism, and the plug board. Let's start up here with the rotors. This machine has 3 of them. This is where the letters get scrambled. Let's take a look at one of the rotors. You have the numbers 1 through 26 for all the letters. So 1 is for A, 2 is for B, 3 is for C, and all the way around until 26 for Z. On the side, you'll see 26 metal contact points. There are also 26 on the other side too. When you put 2 of these rotors together, the metal contacts connect, making it possible for electricity to pass through. On the inside of these 3 rotors, you'll find lots of wires that connects the 2 sides. But as you can see, it's all scrambled. So let's go through the pin for the number 1. Follow the wire through, and it comes out the pin for the number 4. So in this case, an A was changed to a D. When electricity travels through one rotor, it changes the letter once. But remember, we have 3 of these rotors and they each have different wirings on the inside. When electricity travels through all 3 of them, it changes the letter 3 times. Then at the end, we have the reflector. This also has 26 metal contacts. Inside is more wiring that connects the letters in pairs. So it goes in as one letter and then comes out as another letter. To the right of here is the input wheel. It has 26 wires that go in and connects to the 26 metal contacts. Let's put this all together. Electricity flows through one of the 26 wires. Let's say the wire for the letter Y. Then it gets changed to a different letter at all 3 rotors. Then it hits the reflector, which again changes the letter. And then it goes back through the rotors again, which changes the letter 3 more times. And it comes back out on a wire that represents a completely different letter. And if you were counting, this means the letter was changed 7 times. Now, this is just an example of how the letters could get scrambled, but the path can and will change. Each of these 3 rotors can rotate to 26 different positions. When any one of the rotors changes positions, this will also change the path of electricity, making it very difficult to predict which letters are going to come out. The 26 wires from the input wheel travel down the right side of the machine to the plug board in the very front. Now, the plug board was yet another way that the letters could be switched around. Specifically, you could swap 2 letters. So let's say we want to switch the W and the J. You could take one of these cables here with plugs at each end and put one of them into the W spot and the other one in the J spot. On the back side of the plug board, you can see the individual wires going into the tops of each socket and then out to the bottom of each socket. Let's take a closer look. This is the plug board socket for the letter O. If nothing is plugged into it, the electricity flows in through the top, then through the shorting bar, and then out through the bottom. This means that the plug board didn't change the letter. It came in as the letter O, and then it came out as the letter O. When a plug is inserted, it pushes up the shorting bar so it doesn't connect anymore. Now the electricity flows in through the top, out through the top pin of the plug, then through the cable, and out through the bottom on the other side. What came in as an O now comes out as an E. Oftentimes, they would use up to 10 of these cables. Notice how a few of these letters are still left without a plug. Let's take a look at the keyboard mechanism. Each of these keys is connected to a long stem beneath it. They have springs that push them back up when you release the key. The last row of keys have the springs connected at the top. Right next to all of these keys, most of the space is taken up. These are the 26 key switches. These switches are a little bit more complex than just the on-off switches that we saw earlier. Let's take a look at just one of the switches. This one is for the letter P. The switch has 3 different copper-colored tabs. The wires are connected back here, and the flow of electricity is controlled from the other end. When a key is pressed, it comes down and hits the rubber end of the middle tab. What this does is changes where the electricity can flow. Before a key is pressed, the top 2 tabs are connected, and after the key is pressed, the bottom 2 tabs are connected. There are 26 key switches, and here's all the wires that are connected to them. The top tabs are connected to the light bulbs. The wires go to the left and up to the corresponding 26 light bulbs. The middle tabs connect to the plug board. They go through the wires to the right side of the machine and down to the corresponding letters on the plug board. A wire from the battery goes directly into the bottom tabs of each key switch. So each switch has 3 different tabs and 3 different places where they are connected to. Before a key is pressed, the bottom tab isn't connected to anything, so the electricity has nowhere to go. This is true for all 26 key switches. No circuit, which means all the light bulbs are off. Now let's say we press the X key. The battery and the plug board are now connected. This completes a circuit, but it's not as simple as the circuit we saw earlier. Let me show you a quick overview of the path of electricity. Don't worry if you can't keep up quite yet. We're going to go over each part one by one. Let's take a closer look at each step. Electricity flows from the battery to the bottom and then middle tab on the switch for the letter X. Then it goes directly to the plug board, and in this case there's nothing plugged in for the letter X, so it comes back out as the letter X, up the side and into the input wheel, then through 3 rotors, the reflector, and then back through the rotors again, changing letters at each step of the way. What started as the letter X is now the letter K. Now we come back to the plug board for the second time. The letter K is swapped with a C. So in through the letter K, through the cord, and then out for the letter C. Then travels from the plug board back to the middle tab on the letter C key switch. Remember, we started as the letter X, but then came back in as the letter C. Then it goes out the wire of the top tab and up to the letter C light bulb. Then the current flows through the metal light bulb plate to this tiny wire which connects back to the battery. This completes our circuit. As soon as the key is released, no more circuit and the light bulb turns off. So just to recap, once a key is pressed, electricity goes from the battery to whichever key switch was pressed, then the plug board, rotors, then back to the plug board, then the key switch for our new scrambled letter, then the corresponding light bulb, and then back to the battery. The letter is changed 7 times at the rotors, and then possibly 2 more times at the plug board. Remember that the letter isn't always changed when it goes to the plug board. Okay, the electric circuit was the hard part of the video. If you made it this far, we're doing good, but there's a little bit more that I want to show you. Each time a key is pressed, you'll notice that at least one of these 3 rotors will turn. Press a key, rotor turns. Press a key, rotor turns. This means that if you press a key twice, you'll get 2 different letters. In fact, if you keep pressing the same letter, a different light turns on every time. This is what made Enigma so powerful. The code was always changing, so it was hard to predict which letters were going to come out. The way these rotors spin is completely mechanical. No electricity needed for this. Even if the battery was taken out, pressing one of these keys would still turn the rotor. On the bottom of the machine is a large metal plate called the actuator bar. It works like a seesaw or a teeter-totter. Pressing any of the keys pushes it down on this side, which pushes it up on the other side. Around the back side is where the magic happens. This uses a ratchet and pawl mechanism. This is the ratchet gear, and this small piece is the pawl. When the pawl is pushed up, it spins the rotor and then comes back down. You can see how this would spin it in only one direction. This up and down motion will keep spinning the rotors, one slot each time. The next two rotors work a little different. Let's take a look at the second one. Most of the time, the pawl can't make contact with the ratchet gear teeth. It's blocked by an edge around here on the first rotor. The first rotor has a tiny notch around the side here. When the rotor spins, the notch travels around the edge. Watch what happens when it comes up again on the other side. The pawl will fit right into the notch and the second rotor is allowed to spin, but just once. The next time it will be blocked again and only the first rotor is allowed to spin. That edge on the first rotor has to go all the way around before the second rotor is allowed to spin again. This will happen once every 26 key presses. The same thing with the third rotor. There's another edge on the second rotor that has to go all the way around before the third one is allowed to spin. Last but not least, we have the three levers on the very back with index wheels at the very end. They ride along the outside of the rotor gear teeth. This means that the rotors always stop spinning at the next number. This is important so that the electrical contacts always line up between the rotors. Before you use the Enigma machine, it would need to be configured with the right settings. There are 4 of these settings to go through. First is the rotor order. Each Enigma machine came with a set of 5 rotors. Choose 3 of them and then choose which order to put them in. Then there's the ring setting for each rotor, which is basically the shifting of these number wheels, but that also includes the notch on the side. This means this will change when the leftmost rotors can be advanced to the next number. Then there's the starting position for each rotor. You can set this through the tiny windows up here. And the final setting is the configuration of the plug board at the very front. So everyone in the German army had these settings in advance. They were distributed out by paper so they would know which settings to use on which day of the month. Even if the opposing side has their own Enigma machine, they won't be able to read the messages unless they know the settings that were in use that day. Some of the ideas behind the Enigma machine are complex and sometimes difficult to understand. However, it may come easier to those that increase their ability to do math and science. Brilliant.org is a problem-solving website and app that has over 60 courses in mathematics, science, and computer science. The idea here is to learn by doing. They teach you a concept and then immediately you get to try it out in a fun and engaging way. You can use Brilliant to help you as a student in school or as a professional or anyone who wants to keep their skills sharp. There's a wide range of content and they're even adding new courses from time to time. Instead of just learning a formula and blindly plugging in the numbers, you get to visually see why that formula works. There's nothing quite so satisfying as when that light bulb goes off in your brain. I like Brilliant because it shows that learning can and should be fun. You can sign up for free by going to brilliant.org/JaredOwen. Also, the first 200 people will get 20% off their annual premium membership.